Hi, everyone. Hopefully you can hear me. The mic's on. Today I'm going to talk about classical first pathways to early fault-tolerant quantum chemistry. Before that, a lot of the heavy work was done for me by the first few speakers, but I made some cute images, and so I want to show them. Anyway, so why do we want to use quantum computers to solve chemistry problems? Well, we think chemistry problems are exciting and useful and can change the world. So what does that look like? Well, in this, this nice Dr. Seuss-inspired image created by AI, we have several places, and I have a different title for this talk, a version of this talk, Oh, the Places Quantum Will Go, okay? And so we've got different locations. One of them is the rusty coast. Materials fail slowly at enormous cost. And this, costs billions of dollars to the U.S. economy and more generally the global economy every year because cars rust, infrastructure rusts, battleships rust. So that's bad. And even though it affects battleships, really big machines, the things that control it are sort of microscopic. There's a lot of carbon in the air. This causes global climate change. That's not really great. It was 62 degrees in Wisconsin when I left, which was a record high. It was also 1 month ago, it was like -30. So there are huge swings in the temperature. That's not great. Perhaps if we had a catalyst which could capture carbon and turn it into a resource, or at least bury it again, that would be useful and could help one of these grand challenge problems. Oh, wrong way. And finally, in the nitrogen valley, we have fertilizer. It sort of feeds the world, but making it is energy intensive. 3% of the global energy goes through the Haber-Bosch process. However, plants kind of just do it on their own with this nitrogenase. And if we could understand that, perhaps we can design a better process. And so these are three different grand challenge problems, from materials, climate, to agriculture. And what holds them together? Well, there's the common bottleneck of strongly correlated electrons. This sort of whirling specter of trying to solve these problems are really, really hard. We need quantitative accuracy for predictive chemistry so that we can design processes that are efficient and effective to allow us to solve some of these grand problems. Classical methods can be spectacular, right? We can solve a lot of problems, but naively, the cost grows exponentially. Quantum algorithms can potentially save us, but that's only if we can afford the overheads. So it comes down to a question of which algorithms, classical, quantum, neuromorphic, whatever, and at what cost? Because a practitioner, a person who's trying to design a new catalyst, doesn't care where the answer comes from as long as the answer can be verified. Like, you don't want to just ask AI, design me a catalyst, and get whatever nonsense picture they give you. You want it to be rigorous and scientifically valid, but it could come from like a child prodigy, or it could come from an abacus, or it could come from a classical or quantum computer. So where this all comes down to is so-called computational simulation of quantum matter. So that allows me to say materials and molecules. The goal is to predict energies, and as Nicole so rightly said, energy differences, single points don't matter that much, of electrons in materials and molecules. We sort of have, I'm going to talk about two platforms here. Classical, you have various algorithms. Here's a laundry list that you don't have to understand. Full CI, density functional theory, coupled cluster selected CI tensor networks. They all have their pros and cons. Quantum, I sort of put it in two families: NISQ, VQE, variational quantum eigensolver, that sort of family, and fault-tolerant QPE family. Here we're sort of talking about bridging the gap. So there are other things that exist, but there's sort of those are two families one can define. So what is the state of the art? So in current quantum versus current classical, things that were run in November of last year. Okay, today's classical algorithms just totally destroy today's quantum algorithms. It's like not really a race. For chemistry, for accuracy necessary, today's classical algorithms are great. Our group's trim-CI algorithm, you can read about it here, I'll talk about it a little later, required about 5 CPU hours on a boring commodity laptop. A recent NISQ demonstration from IPAM using subspace quantum diagonalization used 72 qubit quantum computer, it's a lot of qubits, also used 10 to the 7th CPU hours on the side. And so there's, from some perspective, there was an expansion of number of determinants. I'll go over it a little bit later. Both the subspace quantum diagonalization and our trim-CI algorithm use that same expansion in different ways, and we're sort of about 1 million times more compact than the SQD algorithm. It's not to say they can probably do better, but that was what was published sort of 2 weeks before we published our paper. Okay, what about on the other side? On the fault-tolerant side, costs are dropping and pretty fast. Katerina had the same plot. If you look at the number of Toffoli gates over time and track it, it went from a century for FOMOCO, a flagship target that would help us understand that nitrogen fixation problem, down to sort of a couple hours. So we went from decades or a century to hours through a lot of performance enhancements on the algorithmic side, but also, as Katerina showed, there were enhancements across the stack. Okay, so that's kind of cool. We could, if that device existed, we could get the answer in less than a day with sort of provable certificates. Where our classical algorithms for the same problem, so this work from Garnet Chan's group, thinks that he can get the answer to chemical accuracy using unrestricted DMRG with a bond dimension of 400,000 for that same FOMOCO molecule in about 23 hours on the world's largest supercomputer. So we have 1 day on the world's largest maybe Frontier's number 2, on one of the top 5 largest supercomputers. By the way, that exists. It's expensive to use, but you can go touch it, versus about 1 day on a quantum computer, which doesn't exist, right? Those were resource estimates. You can't touch that device. And so FOMOCO, which has been a guiding star, the reason we can make this plot here, it's been a guiding star for, 10 years of algorithm development, may not actually be that hard. Or it's really hard, but it's not that hard that we would have to use QPE on a fully fault-tolerant device as the only method to get that. Maybe the classical computer can get it.
So this is for the ground state energy estimate? Or
this is for getting the ground state energy estimate. Both of those are getting the ground state energy to some accuracy. So on one side, NISQ kind of didn't produce great results. On the other side, resource estimates, as we've seen in talks this morning, and in this work for FOMOCO, do not seem that promising, even though we've developed really, really slick algorithms. So what do? Well, let's try to bridge the gap, and we're going to now go into some of the early fault-tolerant quantum algorithms, I'll say, or I hope they're early fault-tolerant. We're still working on them. A lot of the rest of the slides here are speculative work, which I haven't published yet, which means that it could be right, or maybe in a week it could be wrong. But I think they're exciting directions, which are worthy of discussing at a workshop with this. And I really want to get it in front of all of you experts to get your opinions and really sort of make sure we're going in the right direction. On the classical side, we showed this sort of trim-CI algorithm outperformed the NISQ. So what is that algorithm? Well, it's one of a class of selected configuration interaction algorithms. The true wave function is a superposition over this is the wrong ansatz. Is an exponential number of determinants, radically more efficient. So there's an exponential number of determinants. There's so many. There's 10 to the 36. So you can't write them all down. That's silly. But if you include an important subset, forget PsyQ for a second, if you include an important subset, maybe you can pick 100 or 1,000 or 1 trillion, and that small, seemingly vanishingly small corner of Hilbert space might be good. Selecting the optimal set is sort of some crazy NP hard problem, fine. But what can we do? Well, Hao Zhang here, we've been working on the trim-CI algorithm, which uses essentially random stuff to get the answer. You start with maybe your some initial core of determinants. Maybe that's 10, some really small number. 10 out of 10 to the 36th, 10. And then that happens to be connected to a bunch of other determinants by matrix elements of your Hamiltonian. So you can think of it as a walk on a graph if you want. But one determinant is connected to no more than n to the fourth. Determinants by the terms of the Hamiltonian. We expand and pick things that are important that are attached to that initial determinant. Then we get rid of bad ones. We just sort of we trim a bunch away, and we get a final core, which is not as big as this sort of a galaxy of determinants. And we do this over and over and over and over and over and grow. And you can think about this as sort of a walk on a graph. And we usually target like not actually growing very fast. So we'll do 1,000 iterations and get 100 determinants. Yeah.
To make sure I know what you mean by determinant here.
Yeah.
Are you talking about a Slater determinant?
A Slater determinant. Yeah, sorry, a Slater determinant, which for all intents and purposes is a bit string. You can think of it as a bit string. Here, this is just 111,000. It's a bit string of fixed Hamming weights.
It's a list of formulas.
Yes.
So these are fermions.
Yes, these are trying to solve fermionic problems. Yep. Go ahead.
So chemistry problem is actually more structured than what we expected, right? We have the number preserving symmetry.
Yep.
We add on this number preserving symmetry, and also we kind of, if we're starting from the bit string, from a lower excitation.
This is all works within the symmetry subspace, the number preserving symmetry subspace. Because when you start with a determinant, the Hamiltonian is number preserving. It only connects you to other determinants within that symmetry subspace. Yeah.
How is this different from heat bath CI?
Say one heat bath. Yeah. Heat bath doesn't trim. So this actually uses a heat bath step in the middle. But an important thing is we do a bunch of random stuff. Like we pick random determinants as our initial state, whereas heat bath CI, which I was on a lot of the early papers for that, starts with Hartree-Fock and grows from Hartree-Fock. This grows from random determinants. That's why we call it from random determinants to the ground state. And then heat bath CI usually doesn't trim. It just sort of grows unbounded.
How does randomization help you? Is this saying something about the nature of the problem? Like you have a good chance of
Yeah, I don't know. And that's one thing we're trying to study with applied mathematicians who are good at randomized linear algebra is why is randomization so powerful here? And there are some theorems that exist that I can't say I understand, which say that randomization is more powerful than you think. And so this is not the randomization of a quantum Monte Carlo algorithm, so there's no sign problem. Don't let that creep into your mind. This is just pick random bit strings, calculate, find things that are connected to it, walk along this really, really large graph, getting rid of things that are bad. Bad means they don't contribute a lot to the energy when you diagonalize in that subspace, and just try and find a compact space that gives you a really, really good representation of the ground state.
Since you elaborated on this,
yeah.
Anyway, it's only the initialization that's random. Everything else is...
No, there's a lot. There's other random things. So there's this kind of local trim step. We randomly assign determinants into different buckets, and then we diagonalize those buckets independently of each other, and then we take the top k from each bucket and put them together and do another diagonalization. So there's some hierarchical thing, but that random distribution of determinants seems to be kind of important because it allows the determinants to sort of be important all the time rather than just important with their friends, which, again, don't fully understand all the chemistry behind it, but so we have a lot of knobs, too many knobs of the hyperparameters. I tell Hao that when we have too many hyperparameters, it means we don't understand the algorithm. We don't fully understand the algorithm. Maybe Nam, you had your hand up for a while.
Yeah, so this only works if the state that you're targeting is like has a compact support, right? Because otherwise you have to diagonalize over subspace.
That's a subtle question. I can find, so let's just say I had an arbitrary solver that would find the best local subset S. There's always exists the best 100 determinants, right? And I'm searching for those. Whether or not the best 100 determinants is good or not comes down to whether there exists compact support. But the best 100 is a question even if the wave function is really extended.
So there's still room for quantum.
Right, so that's going to be 3 slides, and 3 slides is going to be talking about that, the limits of this. Yes?
So how does the final core size compare to the initial core size?
That's a hyperparameter. So one of the things we have is core set ratio, and a lot of times we go, don't grow, just explore. Just always keep 10 determinants and just snake around, and then every 2 rounds, every 3 rounds, add 1 more determinant. And so we might go 150 or 200 iterations, but only pick up 100 determinants, where we actually touched maybe 1 million or 100 million determinants along the way, but we only kept 100. That's still a vanishingly small fraction of the Hilbert space.
Remind me what you trim on.
What do we trim on? We take we trim on the coefficients we trim on these coefficients. Yes?
Is the problem output here just the energy, and that's all you care about, or?
Yeah. At the end of the day, we're just trying to lower the energy. Yep. And kind of the goal is to find a compact description of the ground state.
So you want both of those things? You want to learn about the ground state?
Yeah, and we find, it's not here, it's in an upcoming manuscript, we find some really interesting things. So for an iron-sulfur cluster, Fe4S4, 100 determinants already distinguishes you between different stripy states. So we can see that there are 4 competing phases of this Fe4S4 cluster with 100 determinants. We can already see, we don't know exactly their ordering, but they're sort of naturally finding different basins. We'll call them basins of attraction. They're finding different basins for the various ground states, which if you extrapolated or you got to the ground state energy, they might be sort of frustrated and have very, very small gaps between them.
I would guess that the quantum algorithm will not give you any state information at all, right? You just get.
You can measure the correlators and things. Yeah. Great.
Random picking can be parallelizable. Can implement it in parallel?
Yes.
Okay.
Yep. And we also run, usually we have, because it's random, we run 100 things in parallel and pick the best one and then go from there. Great. So I like this algorithm. Also, we make cool pictures. We like these pictures. So this is some demonstration where the distance in this space, it's a projected space, is the distance is the distance, the Hamming weight. So it's proportional to the distance of the Hamming weight. And you see we sort of start with some core. This is a cartoon. This is real data. We pick a pool. At the end, we found this middle determinant, which is now bigger because it is more important. So we picked up that one, and we dropped a bunch of crud that wasn't important. That's some sort of example. And for 2 hard problems, these aren't easy problems, an Fe8, so a nitrogenase P cluster, trim CI performs way, sort of 10 to the 5th better than heat bath CI, so it finds compact spaces. And on a Hubbard model, so this is a cool plot. As you go around, that's more determinants. As you get closer to the middle, that's your error. We sort of get to the middle where these other older selected CI algorithms sort of get stuck in the middle. So that's to say we can find compact spaces that are interesting. And this was where we got the ability. The reason we're so much faster and so much better than the quantum diagonalization method is we just found a compact subspace, whereas they were just sampling out of a state. Okay, so what does this mean for, say, quantum algorithms and getting real advantage in chemistry? So this work, which involves Katerina's QPU estimates, and my grad student Hei Zhang from chemistry, she did a lot of trim CI calculations. We went through the sort of, top 6 problems in quantum chemistry on quantum computers. Who knows if they're actually type 6, but cytochrome is a cytochrome P450 is this biologically relevant molecule. FOMOCO is for nitrogen fixation. Ruthenium, two transition states of ruthenium-based catalysts, which Katerina talked about a lot, and these 2 iron-sulfur clusters. All right, so this is a nice plot, a lot of bubbles. What is it telling us? This is the total process time. So that's the total number of seconds integrated over the parallel time. Here is the number of determinants in our trim-CI expansion. And the size of the bubble is the error, our expected error. We don't actually know what the answer is here, but we have some self-consistent checks which can tell us approximately what the error is. And you can say you're wrong about what the error is, but anyway, that's our guess at the error. And so we can see that, everywhere we estimated the QPU, it's faster, just like Katerina's data showed. It's also the size, it's small. It sort of gets the answer. Our current best FOMOCO, which is not as good as Garnett-Chan's DMRG results. We're pushing, we're getting close, but they're not as good. Our best FOMOCO estimates are sort of, our expected error is 10-ish millihartry, and it took a long time. And so if we wanted to make this smaller, we would have to take more and more time. But the QPU kind of is that small in this metric. And so there could be a runtime quantum advantage here. But still, as we've mentioned several times, this is sort of an untenable number of qubits and an untenable number of seconds, especially since this can be trivially parallelized. And that's why we say it's 24 hours on one of the world's largest supercomputers. Yes?
Wait, Matt, sorry, I'm a little confused about which one of these numbers are classical and which ones are quantum.
Correct. So this is a seconds. The bubbles are realized. We went and ran something.
On a classical computer.
On a classical computer. Those are the runtime that we observed to get this expected error on this problem. The diamonds are estimates of a QPU runtime. The different systems have a little spread, and so we can say something like, that's chemical accuracy. The ruthenium catalyst at 100 electrons, 100 orbitals is sort of solved by trim-CI or SHCI more generally. We don't really need a quantum computer to get that, but maybe the quantum computer would be faster. Here, the bubble is bigger, that's where a quantum computer could provide an advantage in accuracy. But maybe I could make this smaller if I had the world's largest supercomputer.
Yeah. Garnett-Chan basically said that yes, indeed, that is possible. Okay.
Hey, Matt,
Yes.
How do you do the diagonalizations? Do you use Davidson?
We're using Davidson. Yep.
Can you use like truncated Davidson and speed up?
Probably. There are different tricks, but we haven't explored all of them.
Yeah. So how do you reconcile this plot with maybe they were showing different things with the one that we saw from Nicole's talk today, where the bar for based on some success metric that includes runtime and accuracy was quite low.
So that was this 1 to the 8th or something. It would be above 1 month of total runtime. Also, this system wasn't included in that data set because it doesn't have a good classical reference. It doesn't have a reference. And so that data set, while powerful, is a bit biased by the fact that we wanted to have a way to verify whether your solution is right or not. So we must have a classical reference. That classical reference has to come from somewhere, so every problem has to be solvable by some algorithm, unless you have some hidden solution thing.
And also, wasn't Nicole's data allowing for parallelism?
Yes.
This one is not.
Correct.
So that's why it's quantum is beating it out, because you could parallelize this a billion times over, at least a million.
Right.
So, Matt, am I understanding this correctly that for the FOMOCO big, it's around 10 million or 100 million CPU seconds for 10 millihartry?
Yeah.
So do you have any guess as to how long it would take for 1 millihartry?
Yes, but and that's going to be the next 2 slides talk about the tail. We call it the tail. Peter.
Yeah, you said that these require too many qubits. What are the?
This is 2,000-ish logical qubits. I think that's about the number. So maybe the ruthenium you know very well, but yeah, some 2,000 logical qubits because it's qubitization and you have all these ancillas to deal with. Great. So what's the problem with TRIM-CI? Why can't the classical algorithm just solve everything? Well, getting more accuracy gets harder and harder. Every time you add another determinant, the gain you get is lower. And so we see this as a power law dependence on relative energy error versus number of determinants. It turns out you can do 1 trillion determinants on classical computers. That's a lot. But we stopped at sort of about 1 billion. And if we look at this plot, right, I got pretty good gain. I half the error. Let's see. I half the error, and it took me 10 to the third more determinants. I half the error. It took me 10 to the third more determinants. If I want to, this is 1% error. That's maybe good enough for a Fermi-Hubbard model. But here I was 10 millihartry error. I need to half it, and half it, and half it, and half it. I got to half it like 4 times, which means I need to go to 10 to the 11th, 10 to the 14th, 10 to the 17th, 10 to the 20 determinants. And so somehow this is a very powerful algorithm for getting to, I don't know, 3% or 1% error, but really pushing it down is hard. And we call this the tail problem internally. And our question is there any way to pick up the tail more efficiently than just more determinants? Add more determinants, you'll get the answer at increasing cost. I think quantum computers can help us pick up the tail in an efficient way. And that's what I'll talk about in the next few slides. Maybe, okay.
I have a question.
Yep.
So when you did the work on the determinant, so did
Yep.
you assume a uniform distribution? Did you roll a dice?
We use heat bath sampling, which is based on the magnitude of the matrix element that goes between them. But we start with a random determinant from space. We sort of uniformly sample to get our first step. But then the graph, the walk is weighted by you can think of the edges, the weight of the edges of the graph rather than just random.
So what's the sort of feasibility ceiling for the number of determinants you could capture with this method?
About 1 trillion.
Okay, so you really can't go too much higher than that.
Yeah, I mean, if you gave me a team of supercomputer experts, maybe I could say 2 trillion. But it's not, I can't get an order of magnitude more determinants. I may be able to compactify the wave function more, and we have work in orbital optimization, which gives us additional gains. But there's always sort of a tail, and it's really hard to get around that tail.
And again, that's with like the biggest HPC in the world.
Yes.
Okay.
Yeah, so I'm interested in determining when this tail problem rears its ugly head, right? Because it seems, at least if you believe, Shan's group, that for FEMOCO, at least like the tail problem is not a problem for at least the biggest supercomputer in the world, right? So clearly, it depends on really 2 things, right? One of them is the accuracy that you need,
yep.
right? And then the number of Slater determinants that you have in your solar system, I would imagine, right? Is what it determines on. So
Yeah.
is there some easy method that you came to know for determining when the tail problem comes up? Or this might be a paper. You can say that's complicated. That's fine.
In this paper, we talk about, we speculate a little bit about algorithmic entropy and the alpha of this compared to some impractical to calculate limit. But if you have 2 different algorithms in the same subspace, you can sort of calculate which one's better by calculating the alpha. So we think about that a little bit, but it's hard to know precisely what the best alpha is, which alpha is the slope of this. If we could change the slope, of course, it would be better. So that slope is what comes down. But the cool, maybe I'm going to call it cool. The cool thing is we can just sort of do a few, and we can get an estimate of slope. And obviously, if I fit here, it would have been bad. So you need to do enough. But 1 million is mundane to do. 1 billion is sort of you need to go to Argonne and use their modest cluster.
You were first. I don't think I was first. Okay. So here, my understanding is that you fix a set of orbitals, and then each determinant is within that set of orbitals, which are included.
Yeah.
It's a bit string.
Yes.
But you could also increase the number of orbitals that you're allowed in the first place. I guess that's not included here.
No, so you're given
a
a fixed number of orbitals and a number of electrons, and you find the most compact in that space. We do generalize this with orbital optimization, where we allow rotations within the orbital space, not with sort of virtual orbitals, not in a CAS-SCF style, but just within the orbital space, and that we find really good compactification of certain wave functions that gives us a better alpha.
But you don't have a handle on how much you're missing by not having like a full. There's an infinite number of orbitals, right?
Right. Yeah. I think we would. It's something we could look at, but we don't have a handle on that right now. Okay. So, how are we going to? Oh, yep. Question.
Isn't the presence of the tail problem also system dependent? Like you could imagine a pedagogical example, right, where it's very adversarial.
It's not clear that you can give me an adversarial example. Some people are trying, and I'm telling them they're wrong. But alpha is system dependent, right? A sort of FOMOCO has a worse alpha than ruthenium catalyst. We can sort of see that, and that comes down to this mysterious how correlated a molecule is. So yeah, we could take a set of molecules which all have the same number of orbitals and same number of electrons and rank them by the alpha they have, and the one that has the worst alpha is the hardest problem, at least for this algorithm. No. This algorithm's 6 months old, and I have a big group, but not that big. All right. So how am I going to solve this tail problem? Well, let's try quantum computers, or let's think about quantum computers. Also, I'm thinking about classical methods. Maybe you can put this in AFQMC or DMC or blah, 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 blah. But here we're talking about quantum computers. So what we need to do is we need to take that wave function, that compact wave function, maybe 100 or 1,000,000 or even 1,000,000,000 determinants, and we need to get it on the quantum computer. That's sort of step one. It turns out loading determinants using a quantum computer scales approximately linearly with number of determinants. Here we use QROM state loading, but you can go to this paper, recent paper, and they have some nice code that allowed us to test 4 different types of algorithms. Because the gain per determinant decays with power law, at some point you should just not load another determinant. You could maybe think about doing 1,000,000,000 determinants and loading them all, but at some point, the cost scales linearly, the gain sort of decays, and so there's some place where we haven't really figured out where that exact place is. It's going to be system dependent and dependent on what you're using it for later. But at some point, you don't want to add more. But this can give you high quality initial states. Those are important for fault-tolerant quantum computing. That's important for QPE. So here we can see, and this is an Fe4S4, 36 orbitals, very, very strongly correlated problem. We get to, say, 1,000 determinants, we get 0.8, but it sort of starts to roll off, and at, say, about 0.9, 10,000 determinants, say it requires about 1,000,000 T-gates. It's a lot to not even start doing anything yet, right? This is just loading it, so still we have to do QPE on top of it. So maybe you want to stop here, and it comes down to sort of detailed resource estimation, which we're working on now to know at what point the trade-off is worth it. But higher overlap is better, but at what cost?
So why using this specific computation framework for the data loading?
Because they released their code, and I can test 4 algorithms. There probably exists a better algorithm to do this, and we could come up with it. But I just want to know for some algorithm, pick one. QROM is sort of linearly, and we can get actual T-gate counts from Xanadu's repo. We can try different things. This is using QDK chemistry. They have the Microsoft's package. They have sparse isometry loading. So this is a different one. This is a much smaller system, 10 electron, 8 orbitals. But what we show here is the choice of classical algorithm is kind of important. MESIS is a different alternative selected configuration and interaction on classical computers. It sort of performs worse than TRIM-CI, and so you need 10 to the 4th gates, and you only get 0.85 overlap, whereas if you use TRIM-CI, 10 to the third, this is total gates, C naught plus T's and blah, 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 blah. You get close to 1 overlap. This says you probably shouldn't use a quantum computer. You already got 1 overlap, so just stop. But OK. This can help reduce costs for QPE, but QPE is hard. We had 2 or 3 talks this morning which talked about how hard QPE is. So can we do something different? Now we have what do we have with us? We have a compact wave function, which has this tail problem. We have the ability to load it with sort of linear cost. So we can get it on the quantum computer. Now we need to do something else. QPE is one option. Are there other options? Now it becomes pretty exploratory. What about imaginary time evolution? So this work is with my grad student at Tarva. Imaginary time evolution takes a good wave function, it makes it better, guaranteed. That's sort of the guarantee. It's non-unitary in principle, so it's sort of hard to do on quantum computers. This double bracket quantum imaginary time evolution, dB-kite, can do this with strictly unitary circuits. It looks like this. UK plus 1, so that's the unitary at k plus 1, is the unitary at k. Then you evolve time evolution. Then you do something reverse. You do a reflection and evolve backwards in time. Then you do the UK again, and then you evolve forward in time. That's kind of cool. It has some structure to it. The bad thing is that the cost scales exponentially with k, because every k calls the underlying k's many, many, many times. So if you have to do too many steps, that's bad. But you approach the ground state exponentially with k as well. So that's kind of cool. But you don't want to do too many k because, I don't know, you have 1 million gate budget or 1 billion gate budget. So what we study here is
sorry,
yeah.
just a question. Does that mean to imply that like the there's a polynomial relationships between k and the accuracy?
Yeah.
Okay, cool.
So there's a double bracket kite kind of has an initial state dependence. If you have a really good initial state, you don't have to take a lot of steps. If you have a really bad initial state, you have to take a lot of steps. So in this study, this is an analytic bound that they derived in the double bracket kite paper. We looked at the required k. Remember, the number of gates is e to this number. So e to whatever that number is too big. We don't want to do 368. So starting with a 0.2 is terrible. But once we get down to, say, 0.9, it's only 15. E to the 15 can be bad, and we haven't fully costed out what that means. But roughly, you can think about it as you have to do time evolution kind of 2 to the 15 times. But this is an analytical bound, and actual k is much lower. They show in their paper, and we're doing our own estimates. So we expect that this might be 3 instead of 15, for instance.
Wait, wouldn't it be 3 to the 15? The structure you just showed me had 3.
Yeah.
Okay, sorry. Okay.
Yeah, I was being vague.
Okay, cool.
Yeah. So if we can get this down from 15 to 3, then it becomes time evolution to maybe time 2 to the 10. We'll call it 1 million time steps, which is about what you have to do with QPE. Or maybe it's a little bit better when you do the full gate counting. So perhaps with a good initial wave function, double bracket kite can be 1 million or 1 billion gates. We haven't finished the costing, but that's one of the directions we're going. Another direction, and I think I have 10 minutes left, but you asked me a lot of questions, so I'm going to go through the next slides a little fast, is what if we use a superposition of classical states, those Slater determinants, which we can compactly get a good 10,000 of them, with quantum states, a set of states stored efficiently on a quantum computer. Okay? So the wave function is a superposition of that. Think of these as trim CI determinants, and maybe there's 10 to the 6th of those. Think of these as they could be unitary coupled cluster singles double states. They could be time-evolved Krylov states. But they exist on a quantum computer, and we're going to use, say, 100 of those. To solve this, you have to, before talking about how to actually do that, I'll just get right to the results. For this 38 orbital 14 electron chromium atom problem, we can look at the efficiency of classical only states versus quantum only states. So the superposition is 0 classical plus all quantum, 0 quantum plus all classical. And you only need about 10 quantum states to get to chemical accuracy. You need 10 to the 5th classical states to reach chemical accuracy. That's just to say the quantum states are way more effective at representing the wave function. However, they're super, super costly. So 10's too much. Can we put those together? Well, without telling you how, just getting straight to the results, we can put them together. And we see this interesting structure. This is the number of quantum states. So we have to, so there's, say, one classical state, which is a degenerate with the first quantum state. Here is where we had about 10 quantum states to get chemical accuracy. Here is just classical states, where we had about 10 to the 5th classical states to get chemical accuracy. Put them together, you get this nice trade-off of Pareto front, where, say, at the elbow, you only need 5 quantum states and 10 to the 4th classical states. So there's a trade-off between the weight on the quantum state and a weight on the classical state. Yes?
Really dumb question. How are you defining classical state and quantum?
Yeah, a classical state is something that is stored efficiently on a classical computer. So it's a Slater determinant. Quantum state is this e to the minus IHTJ on Hartree-Fock. So it's the time evolved from some initial state. So we call those Krylov states.
And the initial state is a classical state.
Yes.
You also would need to solve the generalized eigenvalue problem.
That is the next 7 slides. Yes, I wanted to tell you that it works before I scare you with the linear algebra. So it works, but something that works comes down to what's the costs of doing it, right? You've got the circuit cost here of evolving, and we can say, aha, because we only need 5 quantum states, we have to evolve to less time, so we've sort of halved the resources required for gate depth, but we've added a lot of stuff in the fact that we have to calculate overlaps. And so we have to solve a generalized eigenvalue problem, and that generalized eigenvalue problem has different blocks. You have the quantum-quantum block, so quantum states to quantum states. Do that with a swap test. You have the classical-classical block. This is just, yes? Peter.
Sorry, I think I missed something. So where does the need to, what's the higher level task that
find the ground state energy.
And so, why are you needing to solve a generalized eigenvalue?
Okay, so Canoe solves this problem, hc equals lambda sc. S is the overlap between these wave functions, and generally the quantum states are both non-orthogonal to themselves and aren't orthogonal, are non-orthogonal with respect to the classical states.
Oh, so okay. Tell me if this is right. So you're computing classical overlaps classically.
Yes.
You're not doing that on
Correct.
Okay. Because in principle, you could also
Correct.
use them all on the quantum computer.
But that's expensive.
I don't know.
It is, yeah. That's really expensive because you have to load 10 to the 6th things on a quantum computer and do 10 to the 6th things. And so quantum, we'll do swap test. Classical is just classical information, and it's sort of easy. The interesting part is this quantum classical, and this can be done, you could just call all the classical states quantum states, but then you have 10 to the 6th new quantum things to do. You could also use this with classical shadows. We thought that was going to be a great idea, but it turns out the thing you have to measure is a rank 1 projector, and that sort of breaks classical shadows. Classical shadows don't work very great. So we have another method called the histogram method, where we just reuse shots that we already took. And I'm not going to tell you exactly how that works because for time's sake, but we have a sampling method. Okay, so then this gives us Canoe. The idea is to combine the best classical wave functions with the best possible quantum wave functions to realize advantage over each device. That's the guiding star. Does it work? We're still working on it, but it sort of has a nice structure to it. You time evolve as far as you can on the quantum space. You make as many classical determinants you can on your classical space. You calculate a bunch of overlaps. It's very expensive. I'll show you. And you get something that's strictly not. It has to be at least as good, if not better, than the individual wave functions.
Since you have a lot of control over the classical part, can you choose your classical?
Yes.
Or is it freedom to be orthogonal?
It's very hard. I think it's kind of hard to make it orthogonal to a state that you don't know, because we don't want to do tomography on the state.
So don't. You show tomorrow how to do it? Okay. Sorry. Apparently it's going to get it.
So for time's sake, I will just jump to some estimates of the number of shots. So this comes down, the cost here comes down to estimating these overlap matrices S and these sort of the H version of that, psi, H, psi. So we show here, this is the Frobenius norm of the Hamiltonian. This was done by Jeon Park, a graduate student, versus shots. And we see a great 1 over square root of independence, but as you get bigger, you require more things. This doesn't necessarily, the Frobenius norm is a great measure, but it doesn't tell us the energy accuracy. So we look at the energy accuracy, and it's really noisy and crazy. Why? Because non-orthogonal eigenvalue problems are kind of hard and can be ill-conditioned, and so it's not perfect. But you can see, for chemical accuracy for a smallish system, NH3, we need a total of, say, 10 to the 7th shots. That's not too many. That's not bad. But what if we want to do FOMOCO? At least by our initial data, if we're going to have something in the, this is FOMOCO small, so 108, we need like 10 to the 24 shots. That's kind of too big. We have to make it cheaper. It turns out if you estimated the number of shots to just do VQE on FOMOCO, just one round, it's also approximately 10 to the 24 unless you use tricks. So we sort of get better energies than VQE at the same cost of VQE, but VQE is too expensive, so this hasn't solved all of the problems. We're still working on it. Double factorization can reduce the number of terms in the Hamiltonian you have to measure. That can give you a sort of a reduction. Amplitude estimation can help, and there are sort of other tricks we're looking at as well. But an interesting thing, because we're at IPAM, mathematics, applied mathematics, an interesting thing is the number of shots depends on my eigenvalue solver. It depends on, say, here for H4, using a deflation method, we picked different thresholds for the deflation. And we saw that if we picked sort of a naive threshold of 10 to the minus 5, you might need, 10 to the 7th shots. But if you tune your threshold based on the Frobenius norm of the S, or you use some other trick, you can get a reduction of 1 or 2 orders of magnitudes in shots just from sort of playing with your solver, because the quality of the solver is dependent on sort of the rank of the matrix and how you deal with the ill condition. So I think that's kind of cool and interesting, and I'm trying to get classical linear algebra people to tell me how they solve these better so that I can reduce some of those shots, numbers of shots. So I guess I'm 1 minute from my conclusion. There are a couple questions. How can researchers bridge the gap? I think gadgets from each side. So that the canoe algorithm was somehow sampling in Krylov, but also had some, the time evolution, I would have imagined, is done in a kind of fault-tolerant way, but it's not QPE. Different researchers have different definitions of advantage. Mine is when an application scientist would use the device because it is the best according to their goals. And it's some crazy, their goals are weird. It's a hard optimization of cost, accuracy, time, availability, ease of use, all of things going around to whether your chemist actually wants to use it. But that's when I think quantum advantage is really there. Classical methods are surprisingly good, at least surprising to, I think, many quantum algorithms experts. And quantum methods are surprisingly bad to many classical experts. And so we need to bridge some gap there. Maybe determinant expansions can help. And I think an interesting question is, what can we do with 100 logical qubits and 1 million gates? And I tell my group, try. We can't do it. We haven't been able to come up with it. But that's like an interesting regime where it's hard for me to think that I can break it with some simulation technique. But I also can't figure out how to do chemistry there. So thank you.